Good morning, students. I'm going to continue my discussion on process synchronization in today's class. Before I proceed to the next topic, let's quickly recall whatever we had discussed in the last class. We had discussed about a solution to the critical section problem, which used test and set hardware supported instruction. This solution meets all the requirements that are required to qualify as a solution to the critical section problem. These requirements are mutual exclusion, progress, and bounded waiting. We discussed about Semaphores, which is a software based synchronization tool. It is helpful for synchronizing the execution of cooperating processes. We have binary semaphores or mutex, which could take either true or false as its value, and we have counting semaphores, and we have seen the use of counting semaphores as well. We had also discussed about spin lock or busy wait, which is nothing but processes running on the CPUs getting stuck in a while loop and wasting a lot of CPU cycles. This problem could be avoided if process which cannot go into the critical section is removed from the CPU and pushed into waiting queue, and another process which comes out of the critical section wakes up this process from the ready queue. These are the things that we discussed in the last class. Hope you have understood all these things. Before I discuss about classical synchronization problems and how semaphore could be used to solve those problems, let me demonstrate. I've created two C programs to demonstrate the usage of semaphores. I'm going to run the C programs on the virtual Ubuntu virtual machine which I've created on Windows 10. Let me start the terminal. I have created a library threads in which I have stored the C programs which I have created. This is the name of the directory. Let me list all the files which are there in this directory. Okay, so these are the two files, semaphore.c and semaphore.sch.c. These are the files which I have created, C files which I have created to demonstrate the usage of semaphores. Let me open this file. Here I have created two threads, T1 and T2. For creation of threads, I have used pthread.h library, and to use the operations that could be performed on the semaphore, I have used the semaphore.h library. This has semaphore.h has definitions for wait operations and signal operations. Sem_post is nothing but the signal operation that could be performed on any semaphore. I have taken this mutex as the semaphore. Okay, here I have defined this mutex as the semaphore. If you look at this, this is the routine which I am going to run. Thread T1 will also run this, and thread T2 will also run this. Now what is that I'm trying to demonstrate here is in a time shared system, either T1 could be picked up first for execution or T2 could be picked up first for execution. Whichever the thread which runs this routine should first print entering and get into this part of the code. I'm calling this part of the code as critical section. I don't have any other statements here other than this sleep, which makes this thread to sleep for 6 seconds, and there is one more printf statement exiting. So what I'm trying to demonstrate here is these two threads will not get into this part of the code at the same time. That means whether it is T1 or T2 which is picked up for execution, will first print entering, then get into the critical section, print exiting. Only then the other thread will run this code. The other thread will also print entering first and then enter into the critical section and prints exiting. This is what I am trying to demonstrate here. And what is the initial value of mutex? I have used this function sem underscore init to initialize the value of mutex. I have initialized the value of mutex to 1. This is the method used to initialize the value of mutex to 1. This 0 indicates that this mutex semaphore is shared among the threads which are there in the process. That means it is not shared among the processes which are running in the system concurrently. Now let's see whether this program is going to run as expected. See here, this there is a wait operation which is performed on the mutex, which will make the thread to wait if the value of mutex is less than or equal to 0. Otherwise, it will allow the process to go to the next instruction. Once the process completes its a critical section, while coming out of the critical section, it executes signal that is nothing but this sem underscore post, which will again increment the value of mutex, and other thread can get into the critical section. I do not want to spend more time explaining the wait and the signal operations, which we have already discussed in the previous class. Here I'm making use of those wait and signal operations to demonstrate to you how mutual exclusion of among the cooperating process is achieved. I'm going to compile the program first. Okay, the program is successfully compiled. I'm going to run this program. Observe the output carefully. Now one of the threads has gone into the critical section by printing entering. It will spend some 6 seconds there. Come out, printing exiting. Now the other thread has gone into the critical section by printing entering, and it is exiting. So the threads have run in a mutually exclusive manner. This is what I wanted to demonstrate to you. Okay, let me open another program which also demonstrates the usage of semaphore. Now here we have used the semaphore for a different purpose. Just a minute. Yeah, this is the code. What I am trying to demonstrate here is I want to print this statement first, okay, and then this statement. How I have to ensure that I am printing this statement first and then this, I've created two procedures. This procedure is going to be executed by T1 thread 1, and this is going to be executed by T2. Here I am creating two threads, okay, using p thread create. This is going to execute thread 1 procedure, and this is going to execute thread 2 procedure. I have written two printf statements here. Okay, my requirement is that the statement which is there in the thread 2 should get printed first. So how I am going to ensure that I'm passing 0 as value to semaphore mutex. Okay, so that means whichever thread executes wait first will wait and will not be allowed to proceed. For example, in this case I have written wait here. So if this thread is picked up for execution first by the scheduler, then this thread will not print this statement, and instead it waits on the semaphore mutex. After some time the next thread will be picked up for execution. So here it first prints this and then it executes signal operation. Sem underscore post is nothing but the signal operation, which will increment the value of mutex, makes the value of mutex 1. Then after this T2, the T1 is again scheduled for execution. It sees now mutex as 1, so therefore it uh, you know prints this statement. That's how this is printed first and then this is printed second. This is what I want to demonstrate. So what is that we are trying to do here is we are trying to force a particular sequence of execution of the statements with the help of the semaphore. What are the operations that we are using here on the semaphore? The semaphore here is mutex, which is a binary semaphore, and the operations that we are using are wait and signal, right? So let me see whether we get the expected output. What is the output that we are expecting? This printed first and then this statement is printed. Let me compile the program. What is the name of the program? Semaphore sch.c. Okay. I have typed the command to compile the program. Okay, the program compiled successfully. There's no error. Now I'm going to run this program. Observe the output carefully. This is what we wanted to do. We wanted thread 2 to print the statement. I am in thread 2. This is the second statement first and then this, right? So we have enforced a particular order of execution of the statement. Suppose if you want to change and make this first and this is second, how to do that? Let's see. Let's open the code again and try to do some modifications and see whether that is possible. Now, what are the changes I'm supposed to do? I am supposed to write this wait here, and I'm supposed to write this post here. These are the changes that I have to make to print this statement first and then this statement. Let's say I'll make those changes and let's run the program and see whether what we are expecting happens. Now look at the changes that I have made here. I have commented this and put signal operation on mutex. Okay, this is a spelling mistakes. I will correct it. Okay, hope this works. I will save and yeah, I'll save this program and quit. Let me compile this. Okay, got compiled successfully. I'm going to run this. See now, I'm in thread 1, got printed first, and then I'm in thread 2, got printed. So this is how you can force the particular sequence of execution of statements with the help of semaphores. So I've demonstrated two things here. One is using the semaphore for ensuring the mutual exclusion. That is only one thread goes into the critical section at any given point of time. That means multiple threads are not allowed to get into the critical section. That is mutual exclusion. I've shown how to achieve that with the help of the semaphore, and I have also shown you how you can force the execution of statements in a particular order. Okay, let me now continue and look at some of the classical problems that are there, synchronization problems that are there, which could be solved with the help of semaphores. The use of semaphore for mutual exclusion or to solve the critical section problem could lead to another problem called deadlock. Let's see what is a deadlock. A set of processes is in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in that set. So that means let us assume that we have two processes P0 and P1 running concurrently, and here we have two semaphores S and Q. Let us also assume that they are initialized to 1. The values of S and Q are initialized to 1. So first let us assume this order of execution. Wait of S of P0 gets executed first. It will not stop the process to go to the next statement because the value of S is equal to 1. Now before P0 executes this, let's say P1 executes wait of Q, okay, and Q is equal to 1, so P1 will not wait on Q, it will go to the next statement. Now what happens if P0 or P1 tries to execute this wait? Now P0, if it tries to execute wait on Q, Q would have become, because wait on Q is executed by P1, so Q would have become 0. Wait on S is executed by P0, so S would have become 0. So therefore P0 cannot proceed because Q has become 0. P0 will wait. P1 cannot proceed because S has become 0, so it will wait. Now we have two processes in the set, and both these processes are waiting processes. Now you look at the definition, a set of processes in a deadlock state. Now these processes are in a deadlock state. Why? Look at the definition. Every process in the set is waiting for an event. Now this P0 is waiting for signal of Q and P1 is waiting for signal of S. So these are the events that could happen by these processes, but both these processes are waiting. So therefore there will not be any progress further. If there are only two processes in the system, none of these processes will proceed and system hangs, and this state is called as deadlock state. So no progression happens. Okay, this is the problem associated when we use the semaphore for solving the critical section problem or for achieving the mutual exclusion among the concurrently running processes. The another problem is starvation. You know what is starvation? Starvation, when the process is blocked or not allowed to enter into the critical section, it can go into waiting queue and remain there for a very long period of time. So that's what is known as starvation, not allowed to enter into the critical section. That's known as starvation, and this semaphore could semaphore solution could lead to the starvation of processes. Okay. Now next, let's take up some classical synchronization problems and see the pros and cons of using the semaphore to solve those problems. These are the classical problems of synchronization. Bounded buffer problem. You are already introduced to this. I will again repeat what is a bounded buffer problem and see how a semaphore could be used here. Another one is readers and writers problem. A third one is dining philosophers problem. These are the three synchronization problems we are going to look at one by one and see how semaphore could be used to solve these problems and what are the pros and cons. Okay, I am not defining the bounded buffer problem. You are all aware of it. Okay, we started our discussion, synchronization discussion, with the help of this problem, producer consumer problem or bounded buffer problem. Here we assume that there will be two types of processes. One is consumer, another one is the producer. Producer produces the item and consumer consumes that item, and these processes shares a buffer of fixed size, so therefore it is called as bounded buffer. Okay, now the problem here is the producer should not produce an item when the buffer is full. Okay, and the consumer should not consume an item when the buffer is empty. So that's not possible, right? Consumer cannot consume the item from an empty buffer, and producer cannot produce into buffer which is full. Here we'll slightly modify the solution which we had already uh, discussed. Okay, we will you know acquire, make, force the producer and consumer processes to acquire a lock before accessing this bounded buffer, right? I have written here the uh, producer process structure of the producer process and the consumer process. This is the structure of the consumer process. Sir, I should have written this. This is the structure of the producer. Let us try to understand this one by one. Okay, you see the solution that we have given to this bounded buffer problem. What are the semaphores that we have used? We have used semaphore empty, mutex, use semaphore full. Okay, this mutex is shared between producer and consumer to acquire the lock on the buffer. Okay, before accessing the buffer, it should ensure that it gets the lock on the buffer. Once it is done, producer is done using the buffer, it will release the lock on the buffer. Same thing is done by the consumer also. It will obtain the lock on the buffer, and after it is done with the buffer, it will release the lock on the buffer. Now here what we have to understand is, initially when we uh, start these processes, this empty is a counting semaphore, whereas mutex is a binary semaphore. Now we will initialize the value of empty to n, which means that we have n empty slots to which producer can put the items into, and how many items are there in the buffer, that is indicated by this full, which is also a counting semaphore, and it is initialized to 0 initially because the producer has not produced any item and no item is there in the bounded buffer, so it is 0. Okay, and what should be the value of the mutex? Now you have to tell me. It is a binary semaphore, it is used as a lock, so initial value of mutex should be 1. Okay, whichever sees mutex as 1 will hold the buffer or will get the buffer to update it or to manipulate it. Okay, this you will have to remember. Now let's discuss about the producer first. What happens when wait on empty is executed? Empty is n initially. A producer is going to produce now first item, so therefore the empty value is simply decremented by 1 and it becomes n minus 1, right? That means the producer is now going to produce one item that is going to be put in the buffer. Then the producer, assuming that the consumer has not obtained the lock on the buffer at this point of time, the producer, when it executes wait and mutex, it sees the value of mutex as 1 and makes the value of mutex as 0 and enters into the critical section. Why critical section? Because it is accessing the shared buffer. Now if the consumer also tries to enter into the critical section, it will not be able to do so, because when it executes wait and mutex value has become 0, so it waits. It will not be allowed to enter into the critical section. Now in this, it puts this in this part of the code. We assume that the producer is going to put the item that it produces into the buffer, and while coming out, it will release the lock on the buffer, and it will do the operation signal on full. So now what happens to full? Signal will simply increment the value of the semaphore, so therefore full becomes 1. So thus producer has produced one item and made full is equal to 1. Suppose the size of the buffer is 5, let's say. What happens after the execution of this producer? The empty becomes 4, because one slot is already filled by the producer, and full becomes 1, and this goes on. Now let's see the consumer process, right? In the consumer process, what consumer does, assuming that nothing is there in the buffer, and consumer should not be allowed to consume anything from the empty buffer. So when full is equal to, sorry, it is waiting on the full. Now initially full will be is equal to 0. So therefore the consumer is not allowed to enter into the next instruction. Suppose if there is an item, the same thing holds good for producer also. Initially empty is equal to n. If all the slots are filled by the producer, the empty becomes, the value of empty becomes 0, and producer is not allowed to produce any item into the buffer. So that is achieved with this wait. And here what is achieved, a consumer is not allowed to consume any item if full is equal to 0, which means that no item is present in the buffer. Okay, if full is not 0, it has some value, that means that so many items are there in the buffer, and consumer is allowed to enter into the next line of code, and it decrements the value of full by 1. So if full is 2 items are there in the buffer. After this, the value of full becomes 1, because the one item is going to be consumed by the consumer now, right? Now this wait to executed to get the lock on the buffer. Okay, it is going to consume from the buffer, right? So this lock will help the consumer to access the buffer in a mutually exclusive manner. Then once the buffer is utilized, it will release the lock on the buffer and perform signal on empty. What will happen to the empty now? Empty is simply incremented by 1. Suppose if 2 items were there, how many slots were empty? Assuming that the buffer size is 5, 3 slots were empty. Now the consumer has consumed one more item, so therefore the value of empty becomes 4. So it simply gets incremented by 1. So this is the solution, a semaphore solution for the bounded buffer problem. I hope you have understood. We had given the solution to this problem using test and set instruction, and we had also given solution to this problem I think using Peterson's solution, right? So now we have seen how semaphore could be used for solving this problem. Let's move on and take up the next classical synchronization problem, that is readers and writers problem. Okay, let's see what is readers and writers problem. Let's assume that there is a database which is going to be shared among several concurrent processes. Let's name these concurrent processes as readers and writers. Readers are those processes which only read the database. It means they don't update the database. Writers are those processes which updates the database. That is, they read and write. Read first and then update the database. So there are two categories of processes which are running concurrently, readers and writers. Okay. Now what is the problem? Let me tell you what is the problem. So you have to allow multiple readers to go into the critical section at the same time. It means that it will not lead to critical section problem, or it will not lead to razor own condition, because these readers are only reading the database. Okay, what is critical section here? Reading from the shared database, that part of the code is the critical section, and multiple readers could be there because they only read, they don't update. But only one writer can access the database at any given point of time. Okay, if some reader is reading before the writer tries to access the database, the writer is made to wait. Or if writer is trying to write to the database, then all the readers are made to wait, and all the writers are also made to wait. So that means the problem is allow n number of readers to read from the database, but when some writer is trying to write to the database, no reader is allowed or no writer is allowed. Okay, and multiple writers cannot access the database for updation at the same time. Okay, these are the problems, and let's see how this problem can be solved with the help of semaphore. Okay, before we look at the solution to readers writers problem, let's see the data structures that are shared among the reader processes and writer processes. We are going to define two semaphores, mutex, as I have told you earlier. Mutex is for achieving mutual exclusion, and it is a binary semaphore. It can either have 1 or 0 as the value. Here in this case, WRT is also a binary semaphore, and it can also take 1 or 0 as value. This WRT is shared among all the reader processes and the writer processes, whereas this mutex is shared among the reader processes only, and this read count is a variable, shared variable, that is manipulated by the readers. Why is this required? At any given point of time, the value which is present in this variable, for example, it has 10, means that there are 10 concurrent readers now. Okay, accessing the database for reading purpose only, right? So this you have to keep in mind. As I have told you, writers uses only WRT, not the mutex or not the shared variable read count. Okay. Now with this understanding, let us proceed and see the solution for readers and writers problem. Okay, the structure of writer is very simple. Before any writing operation is performed on the database, or updation operation is performed on the database, a lock is acquired and released once the operation is over, that is writing operation is over. So what is that lock? We have used a semaphore WRT, which is initialized to 1. Okay, so whichever writer, suppose assume that there are two writers trying to access the database for updation at the same time. Now further, let us assume that is W1 is the writer which sees WRT as 1 first. So this weight on this semaphore will decrement the value of WRT and makes WRT is equal to 0 and will not make the writer process to wait. Instead it allows the writer to perform the writing operation. Then once the operation is performed, it will signal on the WRT, which increments the value of WRT, and WRT becomes 1. Now if this wait W2, which is waiting, why it is going to wait? Because this is the one which is going to see the WRT after the W1. When it sees the WRT would have become 0. So the wait operation will not allow the process W2 to enter into the critical section. So it will be waiting. Okay. When this signal operation is performed by W1, that's when W2 is allowed to enter into the critical section. Hence, mutual exclusion among the writer processes is ensured. That means no two writer processes can go into the critical section at the same time. Hope you have understood this clearly. If you have any doubt, please send me the query in the public chat that is now open. I'll be able to answer your questions. Okay, now let me proceed and look at the structure of the reader process. You have to carefully observe the structure of the reader process, which is quite complex compared to the structure of the writer process. Let me go to the next slide. Okay, see here, this is the structure of the reader process. Here every reader uses this semaphore mutex. As I told you earlier, this mutex is initialized to 1. This read count is another shared variable which is incremented by the reader process every time a reader reads the database. Initially the read count will be equal to 0. Okay, assume that now we are seeing the first reader entering into the critical section. What is a critical section? Critical section is accessing the database and reading it, right? So it makes the read count 1, right? Initially the read count will be equal to 0 because no process, no reader process is reading from the database. So this first reader will see the mutex as 1 and makes it 0 and enters into this statement, that is, it makes read count is equal to 1. Now it checks the value of read count. See this, why is this mutex? Mutex is to obtain the lock on this shared variable read count. So when some reader is performing read count plus plus or read count minus minus operation, lock has to be obtained because it's a shared variable. If you allow multiple readers to access this shared variable, that might lead to race around condition, which we have already discussed when we started the discussion on process synchronization. Now if this happens to be the first reader, then the value of read count will be equal to 1. If it is equal to 1, what we have to do? Now this reader should ensure that no writer writes into database after the reader starts accessing the database for reading. Otherwise there will be a chaos. So this first reader is going to execute this wait on WRT. If any writer is already there in the critical section, that is, if it is already trying to write to the database, this WRT would have become 0 and this reader will wait. Otherwise the reader is allowed to go inside. Now it is done using this shared variable read count, so it can simply release the mutex. If some other reader wants to enter into the critical section, that is, wants to read the database, can do so by acquiring the lock on read count. Okay, then the reading is formed. Now this is reader 1. Now if some other reader R2 is trying to enter into the critical section or read from the database, it can do so. Mutex has become 1, so it will simply increase the read count to 2. It is not the first reader which is entering, so the first reader would have ensured that no writer is allowed to enter into the critical section, so it will simply execute the signal mutex so that another reader can come into the critical section. So what is that we are trying to ensure here is we are allowing the multiple readers to read the database. This will not cause any problem because the readers will not update the value of database, right? Now when the reader is coming out, it will execute the wait on mutex, and if mutex is 1, then it uh, captures it, it makes it 0 so that no other reader can access this shared variable read count, decrements the value of read count. So one reader is going out, so it makes the value of read count is equal to. If the read count is not equal to 0, that means some other reader is still reading from the database. Okay, so if read count is equal to 0 after read count minus minus means that the last reader is going out of the critical section, so therefore it should now should not block the writer if it wants to write to the database. Therefore it performs signal on the WRT and WRT becomes now 1. Any writer can now get into the critical section, or reader can get into the critical section without any issue. After that it executes signal on mutex, which will release the lock on read count. Okay, now if the read count is not equal to 0, this signal on WRT is not executed, simply this is executed so that some other reader can join, but no writer can go into the critical section. That is, it cannot update the value of it cannot update the database. That's what I'm trying to tell you, because the one reader is already there in the critical section. Okay, if you allow any writer to write when reader has already read the database, then there will be data inconsistency issue, so therefore that is not permitted. Okay, so this is how the writer looks like. So we have ensured that uh, multiple readers can access the database simultaneously at the same time, and if some reader is accessing the database for reading, no reader can get into the critical section, or if writer is accessing the database for writing, no writer or reader can get into the critical section. Okay, because if some writer is already there in the critical section, this wait will make the reader process to wait on the semaphore WRT. I hope this solution to readers writer problem is clear. Okay, now let us move on and see the last synchronization problem, and which is very interesting, and see how semaphore could be used to solve that problem. Let me explain this problem. It is an interesting problem. Okay, here what we have modeled is a problem of allocating the resources among the processes in a deadlock free manner. Okay, so what we have modeled is this problem, right? Instead of resources, we have taken chopsticks and in processes. These philosophers are processes. See, here we have considered 5 philosophers: P1, P2, P3, P4 and 5. Who is a philosopher? Philosopher is one who eats and thinks. Okay, he is either in the state thinking or in the state eating. When he is thinking, he is not eating. When he is not thinking, he is eating. Okay, these are the only two things that are done by these philosophers. There are here 5 chopsticks, 1 2 3 4 and 5, that means there is a serious, every philosopher needs 2 chopsticks, so therefore there should have been 10 chopsticks, but there are only 5, which means that these philosophers have to share these chopsticks, right? So that is the root cause for the issue. Okay, so philosopher, when they are not thinking and they feel hungry, they grab the spoons that are next to them, that are to the left, that is to the left and to the right of the philosopher. For example, if P1 wants to eat, he would grab the chopstick 1 and chopstick 2. Okay, but this 2 is shared between P1 and P2. What if P1 and P2 tries to eat at the same time? That is the synchronization problem, right? Now let's see how this problem can be solved. In fact, mutually allow philosophers to eat in a mutually exclusive manner using the limited chopsticks that we have, right? Okay, this is the solution to the dining philosopher's problem. Before I explain you the solution, let's mm, assume that each chopstick represents a semaphore, right? There are 5 chopsticks, so we will have to have 5 semaphores, and all the semaphores are binary semaphores. That means they can take either 0 or 1 as the value. Now how do we achieve that? We have an array chopstick of 5 and all the elements are of type semaphore, which can take either 1 or 0 as the value. Now we further assume that the elements of this array chopstick are initialized to 1. That means all the chopsticks are free to start with, and any philosopher could pick up the chopstick, right? Um, Before this, let us go and see the solution and come back and discuss about this, right? Now let us see the solution. Now you see, uh, any philosopher who is trying to eat should get 2 chopsticks, right? Now for example, let us go to the previous slide. Suppose, let's say, now he is the philosopher who is trying to uh, eat. Okay, P2 is the philosopher who is trying to eat. So what are the chopsticks that he needs? 2 and 3, right? So the philosopher 2, the value of I is equal to 2, means that the philosopher 2 is trying to eat. So what are the chopsticks that he has to get? Chopstick of I, that's 2, and chopstick of I plus 1 modulus of 5. 2 plus 1 is 3, 3 modulus of 5 is 3. Okay, now these are the 2 chopsticks that the philosopher 2 has to get. So he performs weight on these 2 chopsticks. If chopsticks are available, then chopstick of I will be equal to 1, and chopstick of I plus 1 modulus of I will also be equal to 1, and he gets both the chopsticks and he eats. After he finishes eating, he releases. How does he release a chopstick? By performing the signal on that particular chopstick. For example, if he is holding 2, he would have made chopstick of 2 is equal to 0. Now he is incrementing chopstick of 2 to 1, so that some other philosopher can pick up this chopstick, right? And he is going to signal on another chopstick. He is going to release another chopstick. Then he starts thinking. This is how the structure of a uh, you know solution to the dining philosopher problem looks like. Now, there is a problem associated with this kind of a solution. That is, the solution guarantees that no two neighbors are eating simultaneously. How does it guarantee that no two neighbors are eating simultaneously? For example, let's say now P2 and P3 are the philosophers which are trying to eat at the same time. P2 wants 2 and 3 chopsticks and P3 wants 3 and 4. Now either P2 or P3 will first pick up 2 and 3. That is, let us assume that. Okay. Now weight on uh, chopstick of 2 for P2 is, let's say, successful, and chopstick of 2 is made 0. That semaphore is made 0. And similarly chopstick of 3 is also made 0, right? Okay, now P3 is trying to enter. If it wants to get the chopstick 4, it can get, because chopstick of 4 is equal to 1. So let's say it gets chopstick of 4, but when it tries to get this 3, it has been made 0. That semaphore, which is associated with this chopstick, has become 0. So P3 has to wait. It will not be able to eat. So therefore, only one process is allowed to eat at any given point of time. That is the critical section, right? Only when they try to eat, then the problem arises. If they are not eating, then they are not using the chopstick, and there will be no problem at all. Right? This is what is the solution. But this solution could lead to a deadlock. How? Well, let's look at that. Let us assume, okay, you see, you look at this solution first. You keep this in your mind. Now, the philosophers are picking the chopsticks one after the other. This you keep in mind. Let me go to the previous slide which had that philosopher's picture. Okay, that is this. Now, what could happen is, now let us assume this P1 picks up his left chopstick. Okay, and before he picks up his right chopstick, this P5 picks up this chopstick. Okay, this is now with the P5, and similarly it goes on. Now this chopstick is picked up by P4, and this is picked up by this P3, and this is picked up by P2. Now everybody, all are interested in eating, and everybody is having one chopstick in their hand. Now P2, if he has to continue eating, he should get this chopstick 2. P1, if he has to eat, he should get this 1. But that is not released by P5 because he is not getting this. Okay, so there is a kind of circle which exists, right? P1 waiting for P5, P5 waiting for P4, P4 waiting for P3 to release release the chopstick that he is holding, and P3 is holding waiting for P2 to release the chopstick he is holding, and so on. So this will lead to a deadlock. There will be no progress, as none of the philosophers will release the chopstick, because they all of them are trying to get the chopstick which are held by other philosophers. So this is what is the deadlock problem. So the solution that we gave to the dining philosopher problem suffers from what is known as a deadlock issue. Hence this solution cannot be accepted. So we will have to have a deadlock free solution. Okay, so let's discuss about that deadlock free solution in the next class. Before I stop, let me just tell you the problems that are there with the semaphore. Okay, and these are not actually the problem with the semaphore, but let's say an ignorant programmer or unknowingly a programmer committing an error like this. So you know, first he's changing the order of operations that are performed on the semaphore mutex. Actually we should, every process should perform wait on mutex first and then signal to achieve mutual exclusion. Whereas here what is happening is the wait, instead of wait a programmer has written signal, instead of signal the programmer has wait. So this will cause multiple processes multiple processes to go into the critical section at the same time. Okay, so sometimes what may happen is that instead of signal, programmer might write wait. So there is one wait here, there is one wait here. So processes could get into the deadlock in this case. So we'll have to be careful when we are using the wait in the signal operations. They have to be there in the particular order only, and we cannot omit wait or signal. If we do that, then it will take the processes either into a deadlock state or end up allowing multiple processes to enter into the critical section. These are some of the problems which could occur when the programmer is not uh, writing the order of wait and signal operations properly. So to solve this problem, there is one more synchronization tool that is available, which is called as monitor. I will discuss about the monitor, and I will also discuss about a deadlock free solution to the dining philosopher's problem and how that could be implemented with the help of monitors. Let me stop here. I hope you have understood whatever we have discussed in today's class. Semaphores are very, very important and useful tools for achieving the synchronization among concurrently running cooperating processes. Let me stop here. Thank you very much.